In this video, we're going to talk about finding absolute extrema, so absolute maxes and absolute mins. Now, in the past with our work in graphing, we found relative maxes and relative mins, but those mean that they are dips and peaks in our curve. So it was a place where the graph changed direction from either increasing to decreasing or decreasing to increasing. Whereas these values that we're finding are the absolute highest and absolute lowest points on the curve, either in a particular closed interval or in an open interval. So we're going to start taking a look at a function on a closed interval. So we're going to look at a curve of a function, and we're just going to chop it off on either side and look between those endpoints to determine what the highest and the lowest points are. So the extreme value property helps us to narrow down what points to consider. What the extreme value property says is that if you have a continuous function on a closed interval, then it will have its absolute max or min at either the endpoint of that interval or at a critical number within that interval. So graphically, if we take a look at what that is saying, let me just sketch a little curve here. So suppose that I just have a curve that looks like that. And what we're going to do is chop this curve off and look at a particular interval. So for example, I might pick a spot here and call that one of my endpoints. And then I'll pick a spot over here and call that my other endpoint. So we're only looking at the curve that lies between this endpoint and this endpoint. So we're only considering this portion of our curve. And we want to try to find the highest point and the lowest point in that interval. So you can see that what the extreme value property is saying is that the max or the min will either occur at one of these endpoints where we've chopped the curve off, or it will occur at one of these relative extrema, one of those critical values. So in this case, it looks like, well, it's kind of hard to tell here with the endpoint and that critical value, but either one of those is going to be my absolute min, whereas up here at that endpoint, I'm going to have an absolute max. So let's take a look at the steps for determining this without having to sketch the curve. So what we want to do is first find those critical values that lie in that interval. So that would involve finding the first derivative, finding those critical values, so setting the first derivative equal to 0 and solving for x. And then we're going to eliminate any x's that don't lie in the given interval. Then we're going to find the y values of all of those critical values that are in the interval, along with the endpoints of the interval. And the largest y value is going to be my highest point, so my absolute max, and the smallest y value will be my absolute min. So let's take a look at an example. So here I've got a function and my closed interval from -1 to 2, and I want to determine the absolute max and absolute min. So we start with step number 1. I want to calculate my derivative. So my derivative would be 3x squared plus 4x minus 15. And then step number 2, I want to find where this is equal to 0. So I want to find those critical values. So that means factoring this out. So this will factor into 3x and x, and it looks like I'll need a 3 here and a 5 there, so that my outer gives me 9, my inner gives me 5. So I want that positive and that negative. So my critical numbers are x equal to 5/3 and x equal to -3. Now the next thing that I want to do is compare that to the interval. Remember, I'm only looking at this curve between -1 and 2. So either any of these critical values that I have that I want to get rid of, I want to get rid of them now so that I don't consider them. So starting with 5/3, 5/3 lies between -1 and 2. So I keep that one. -3 is outside of that interval. So I'm going to eliminate that critical value from consideration. Now, step number 3 is we want to form a little chart of y values. So step number 3, I'm going to create this little table of x values to consider, and I want to find the y value. So if I list all of the x's that I'm going to consider, I'm going to consider the 2 endpoints in my interval. So those come from here. And I'm going to consider any critical values that were in that interval. So I'm going to consider the 5/3. Now what I want to do is find the y values for each of those. So that means, remember, for y values, we're always placing our number back into the original function. So I'm going to start by putting -1 into the original function here. And if I do that, I get a value of 18. Then I'm going to replace the 2 into the original function. And in the original function, when I place 2 there for x, I get -12. And finally, I want to go to the original function and replace the x's with 5/3. And if I do that, I get, rounding off, I get -12.8. So now that I have all of my y values, I can classify the absolute max and the absolute min. So my absolute max is going to be the y value that's the largest, so that's this one here. And my minimum is going to be the y value that's the smallest, which is that one there. So I can write out that the absolute max for this function on that interval is at -118. And I know that the absolute min for this function on that interval occurs at 5/3, -12.8. Next, we're going to take a look at an example where I want to find the absolute extremum on an open interval instead of a closed interval. So there's a little bit of difference in the steps that I follow when my interval is open, because there might not be an absolute max or an absolute min. And if the function has an absolute max, it's not going to have an absolute min. And if it has an absolute min, it's not going to have an absolute max. So if you think about what that looks like graphically, if I consider the graph of a function, I'll just kind of draw the same thing we had before, only this time when I'm considering the interval, I'm going to kind of chop off the endpoint here, but I'm going to leave the other endpoint open. So the portion of the curve that I might be looking at would start here and then go on forever in that direction. So in this case, because that curve rises forever and ever, it's never going to have an absolute max just on that particular interval. But it would have an absolute min, and that absolute min would be this lowest point here. So that's why you're not going to have both, because in one direction the curve is either going to be climbing or it's going to be heading to a y value of -infinity. Okay, so how do we find it? Well, for one, if I only have one critical number, now in this case I had 2 critical numbers in that interval, there would be one there and one there, but it is possible that I have only one critical number in that open interval that I'm looking at. So if I only have one critical number, I can't compare y values because there would be nothing to compare it with. So I have to use something else when I only have one critical number to determine whether it's an absolute max or an absolute min. So that's where the second derivative test comes into play. If I only have one critical number in my interval, then I need the second derivative to determine if that particular spot is a relative max or absolute max or absolute min. Now the way we do that is that we are going to have an absolute maximum if my second derivative is negative. Now think about why that is. Remember what a second derivative being negative means. If my second derivative is negative, remember that meant that it was concave down. So if I draw a concave down parabola, it naturally forms an absolute max in the curve. Whereas if I have a second derivative that is positive, and I draw a parabola that's concave up, then it naturally forms an absolute min. So knowing whether my second derivative is positive or negative will indicate whether that one critical value was an absolute max or an absolute min. So let's take a look at an example. So here I'm asked to find the absolute extrema for this curve on that open interval from 0 to infinity. So step number one, again, like the other example, I need to find the critical values that lie in this interval. So I will need my first derivative. And actually, if I look at my function, this second term, 32 over x, I'd like to rewrite that in order to use my power rule. So I'm going to pull that x up with the 32, making it 32x to the negative first. So that'll make it easier to calculate my derivative. So my derivative is 2 minus 32x to the negative 2. Now I want to find the critical value, so that means setting that equal to 0. And I'm going to drop that x back down to the denominator because I don't want to solve the equation with a negative exponent. So I'm just going to move this x to the denominator, make its exponent positive, and now I can solve this equation for x. So to solve a rational equation, I'm going to multiply everything in that equation by x squared in order to clear that denominator. So x squared times 0 is 0. 2 times x squared is 2x squared. And 32 over x squared times x squared would just give me 32. And then I can finish that by factoring out the 2 as the greatest common factor, and then factoring this as the difference of two squares, x plus 4, x minus 4. So I've got two critical numbers, -4 and +4. And just like in the previous example, I want to compare those numbers. So I want to compare -4 and +4 to the interval that I was given and eliminate any that are outside of that interval. And since -4 is outside of that interval, I'm going to eliminate that critical number. So I only have one critical number, x equal to 4. So since I can't compare it to any other y value, I'm going to use the second derivative test to determine whether that is a max or a min. So I need my second derivative. So remember, here's my first derivative. So I'm going to take the derivative of that. So the derivative of 2 is 0. And the derivative of this second term would be 64x to the negative third, or 64 over x cubed. And I want to determine if I replace that x with 4, whether I would get a positive result or a negative. And of course, if I plug in 4 for x here, I'm going to end up with a positive result. And a positive second derivative implies concave up, which forms a min. So that means that 4, along with its y value, is an absolute minimum for that function on that interval. Now, if I replace 4 back into the original function to find the y value, I'm going to get 8 plus 8, so my y value would be 16. So there's my absolute min.